Hi folks, good to see you back. So you've made yourself a probe. Now what? Let's take a look. So there it is, your brand new probe. I think the issue with these things is that in order to get the best accuracy out of them, you've got to do some testing. We need to know what this system, this kinematic system, is going to work like before we can actually use it to make accurate measurements. And I say that for a couple of reasons. Firstly, the ball diameter on the end here should be 6mm. It's actually, with my approximators here, it measures at 5.94. So it's less than 6mm. That's important. We need to know that to start with. The diameter of the ball is going to affect the accurate measurements. Also, with these things, there's a certain amount of movement before it actually triggers. I think on the previous video you've seen it's not very big, but it's there and it's significant. So we need to know how far it will move before it triggers. And I think the other thing that we need to know is, because it's a three-pronged probe device in here, the effective trigger point will not be round. It will be lobed with 3 points on it, I think. And I don't know whether that's going to be a significant factor or not. And the only way to find out is to test it. So what we're going to do is put this in the spindle of the mill, and we use the mill to do the testing. I'll then dial out the eccentricity in the ball using the 4 grub screws at the top, and then we'll do some testing, and we'll test it for how far it moves before it triggers, and we'll rotate it round 30 degrees and do the same thing. And I've made myself, I laser cut a disc with, and you really will not be able to see this very well, but there's 30-degree increments around this, and it's also got notches every 90 degrees, so and it's also split because I'm a numpty. But we can use this to index this thing round every 30 degrees, so we know we're producing an accurate plot. I've marked my index disc with 30-degree increments all the way around. The hole in the middle is just big enough to clear the end of the R8 collet, and what I'm going to do is fit the touch probe and trap this disc, and I'm going to align the 0 degree roughly with where the phono plug goes in. So if I trap that in, i.e. just close the drawbar, so as you can see there's a fair amount of wibbly wobbly in that probe tip. Full disclosure, it's taken a good half an hour to get this sorted, but there we go. As James pointed out in the last video in the comments, this is a half thou indicator, so I think the deviation there is probably, what is that, 1/4 of a thou? No, 1/8 of a thou, something like that. In metric we're talking about half a micron. I'm using an indicator on an arm, and I'm just using it for the pointer. I don't need the gauge, I just want it to point to the index marks on this plate. So having lined that up at 0, we can move on to the next bit. The next part of the setup is I've got my micron, this is thousandths of a millimeter, 1 micron indicating micrometer. Don't know how accurate this thing is, but as long as it's repeatable, that'll be good enough, I think. As I advance the thimble, you can see I can push the probe stylus. So the first thing we need to know is when the anvil here touches the probe stylus. So I'll get my DMM and I'll just connect it up so that we can hear it beep when it connects. I've connected my digital multimeter up, and if I advance the thimble again, there we go, back it off and have another go. Right, that's right on the point. Yeah, that's the actual point where it's just about connecting. So if I reset my micrometer there we go, back it off, and we should be able to try that again. You see, we're dealing with tiny increments here. Okay, I'm happy with that. Now we know that advancing the thimble until we hit 0, that's where we actually make connection with the probe tip. So now if I plug my DMM into the actual probe output, so now I can advance the thimble. When we hit 0 on here, we know that that's the point where we've touched the ball, or the ball on the stylus, and then it's a question of how far we go before we make the break. There we go, about 0.017 of a millimetre. So what I'm going to do, and I'm going to do this off camera because it's going to take me probably the thickest end of an hour, I'm going to repeat this operation 5 times and record each result, and then I'm going to index the probe round 30 degrees and repeat it, and I'm going to go all the way around till I've done 360 degrees. Once I've done that, then we can tabulate the results and hopefully do a polar plot and see just how accurate this thing is. After what seems like an hour and a half, I have done all my testing and tabulated it. I've averaged each set of readings. So along the bottom here I have, I'll put a screenshot of this up, but I have the average for each angle. And from that I've averaged them all of the average of averages, and that is the average trigger point is 42.733 microns, and the deviation between the maximum and minimum is 20.6 microns. So it's pretty accurate. And if we look, I've done after a great deal of messing around because I'm not very good at Excel, there's a polar plot of the how accurate it, or when it triggers. The closer this is to a circle, the better. But as you can see, there's roughly 3 lobes, and that is down to the fact that the probe, the kinematic probe system, has 3 touch points. So I mean, you can see roughly they're 120 degrees apart. So that is, I think, a relatively typical response for this type of probe. I haven't gone to all that trouble of manually testing the probe. Very interesting to see that it shows that a basic tri-lobed response curve. We need to do some automated testing, and this is as close as I've got to a proper setting ring. This is an old ball race. I don't even know where it came from, but I have looked at it and it's as round as anything I've got. And we're going to use my internal bore gauge and gauge blocks, and I'm going to find out exactly what the internal diameter of this is, because I need it at I need to know as accurately as possible. So I'm going to have to use gauge blocks. What I've got is gauge blocks between 2 parallels clamped with a toolmaker's clamp, and I've set my bore gauge here so that reads 0, and then I've done the same with my bearing that also reads 0. So from that, all I need to do is add these up, and that will tell me exactly what the diameter of this is, and it says 25 mil. So 25 mil it is. But if I measure it with my approximeters, which zero out, it comes at 24.95. So that shows you how far out these things can be. I'm using this probe wizard by vers.by. So you'll have to go to their website and download it and install it on your machine if you want to use the same. Right, so that's the active screen, and the probe is plugged in. So if I just press the probe, there you go, you can see I'm activating it. From the top, this is the search speed. That's how fast the probe moves when it's traveling fast. Once it's touched the work and come back and then creeps forward, this is how fast it creeps at 10 millimeters per minute. The 40 is the search distance. That's how far it goes before it triggers alarm that it didn't touch anything. The latch distance is how this one here, the one, that's how once it's first made a connection with the part and it backs off, that's how far it backs off, 1 millimeter in my case. This is the effective probe diameter, and I've been fiddling with this, so what we're going to do is we're going to set that to 0. Oops. If I can get that, 0, enter. Then you've got a couple of clearance distances, the clearance distance from the edge and the offset from a corner or a radius, and this one is how far, the last one is how far down it pushes the probe to do a search. So in this case we want that as 0. Right, I'm not sure if this is going to be particularly clear on camera, but I've parked the probe in the middle of my ring, my bearing, and I'm not distorting the bearing because I'm applying pressure to the outer ring, and it's on the top of my vise, and you can still rotate the inner race. So yeah, this is the setup I think for trying to measure, or the best setup I can come up with for measuring the diameter inside here. We know what the diameter is, we know what the diameter of the probe stylus ball is, so we can subtract the result that we get on the by probing this, subtract the diameter of the ball, and we should end up with the right diameter of this part. This is the internal diameter measuring function, so if I press that, after the first pass, it's given us the X dimension, the Y dimension, and the average of those two, which is the diameter at 19.168 mil. I will repeat this, make a note of these numbers and repeat this 10 times, and then we'll take an average. After a few minutes of testing and documentation, I have got an average diameter of 19.1705 millimeters. After a fair bit of experimentation, this is what I've found. I measured the stylus diameter, the ball bearing on the end of the probe, 5.95. We know that the bearing diameter is 25 because we measured that as well. The probe pre-travel from the previous sheet, 42.7. That gives us an effective probe diameter of 5.85, which is the diameter of the stylus minus 2 times the pre-travel, minus the maximum deviation. That is the maximum, the most sensitive minus the least sensitive. If you use the mil to measure the diameter of the probe, you end up with 5.834. And my calculated and mix of calculated and experimental is 5.85. So the difference between those two is 17.5 micron. That's the error that I've got between the two setups, doing it sort of manually and automatic. Yeah, I think in all honesty you could skip all of the pre-testing that I did and just put your effective diameter of the probe as 0 into the probing software, measure it a few times, average it out, and then you will get your average diameter there. That's the easiest way to do it. There we go. I think I'd buy that. That's within the tolerance of the machine. The mill's got a tolerance of 0.02 of a millimetre, so we're measuring beyond its capacity. Let's try and measure this 30mm gauge block that's in the vise. There we go, it's come up with 29.96. That seems to be about the reasonably consistent of that, 26.97, 26.98. What I've got here is a bunch of gauge blocks under what I'm going to use as the reference surface, which is the bottom edge of the spindle. This is ground flat. So I've brought the head of the mill down so that it is, according to these gauge blocks, 120 millimeters above the table. So let me just zero all of these to start with, and then I'm going to put Z at 120, enter. Put the probe back in. There we go. Okay, DMM. Now I can jog down until I break that connection. Oh, there we go. We can simply read that number. That is the length of the probe when it's activated. I am going to jog up and take the probe off. And you might think, why am I doing that? Because I'm going to repeat that test without the probe on. So the net result is subtracting the length we've just set from the length I'm just about to set, will tell us exactly how long this probe is. But more importantly, it will tell us exactly how long this probe body is. So that when I replace the next probe, because I'm going to make some other types of probe, all I'll need to do is enter add the length of the new probe to the length of the body, and I don't need to do this test each time. That gives me a probe body length of 81.095. Happy with that. So I've got two measurements, the one with the probe with the tip, the stylus screwed in, and one without. So subtracting one from the other, I end up with 47.93. So just as a sanity check, bearing in mind that I can't measure this exactly accurately because I can't measure from the centre of this to the centre of this because the thread's in the way. Let's just check with the approximeters and see what we get. So bearing in mind this is not going to be that easy. 47.93. Yeah, there we go. I think I'd buy that. That's pretty damn close. Okay, some final thoughts on this. It's definitely worth doing. It's taken, I guess it's taken me probably a month to actually build it and test it, and a week or so to sit and think about how to design it. So it's taken a while. However, it definitely seems to be worth doing. And but I think there's some important information you need to keep to hand with one of these things. Now we've established the length, the gauge length, if you like, of the probe body. I need to make a measurement each time for the new. Every time I put a new probe in, I should say, I need to know the length of the probe. Then we can adjust the overall length of the probe so that it's still accurate. The other thing is, I think the ball on the end, what I'll do is work out, in fact I'll put it as an overlay, work out the diameter of the ball less the with the correction factor that you'll need to apply. So if you use a ball of a different diameter on another probe, you know how what you need to add or subtract to the diameter of the ball in order to make it read accurate again. That means that you won't have to get your old gauge ring out and test it each time, and you won't need to do the plunge test that you've just seen me do on the Z-axis. So you should just be able to put it in, check for run out, and adjust for run out, and you should be good to go. So yeah, thanks for watching. It's been a really interesting project, this. I do think that as hobby engineers we could probably do better than this. I do think that there are probably other techniques that you can use, or other scientific principles you can use to make a far more accurate instrument. But having said that, for the kind of level of accuracy that most of us can achieve in the workshop, I mean, my mil is 0.02 of a mil repeatability. It's more accurate than that, but that's its repeatability. One of these probes is good enough. So yeah, thanks for watching. Do hit the bell and subscribe banner, and we'll see you on the next one. Next time I hope to make some really cheap probes. So take care, see you next time.